For example 5, we're looking at a definite integral. So I have bounds of my integration. So these represent the left edge and right edge of the area that I'm going to calculate. So when I'm integrating this, I have to look at this integral. And then when I look at this, there is no standard integral for this. I can't apply power rule here. So really, I have to rely on substitution. And there's not much choice for substitution here because the only inside function really is x squared. So I'm going to start with that. I'm going to let u, the inside function, equal x squared. And when I calculate the du, my du is going to end up being 2x dx. And I can see that on the outside, yeah, I have an x dx. I just have to account for that extra 2. So I'm just going to move it over and make it into du over 2. And there's my x dx that will replace that dx in the expression. So writing my integral then, because my endpoints are now in terms of x, but now they're going to be, I have an integral with u, I should make sure that I change my bounds of integration in terms of x, and then my integral then is now, I could rewrite it in terms of u and not have a conflict with my bounds, the variable of my bounds with the variable of my integral. Okay, so then I have to replace the x dx with a du. So I'm going to do du over 2, but that over 2 I'm going to put on the outside because I don't want that to mess up my integration. Now I can integrate this with respect to u. So the antiderivative of sine is negative cosine. And I have my bounds are going to be from, putting my u in here. And then my bounds are still in terms of x, so I need to make sure that I make them from x is 0 to x is pi. I can change the x values into u values using this equation. Now, probably better to just keep it in terms of x and then replace that u in my integral. So I'm going to end up with negative 1/2 cosine of, instead of u, I'm going to replace my x squared back into the equation. Now my bounds and my variable match, so I'm just going to make this 0. I don't need the x equals anymore, from 0 to pi. Okay, and then once I do that, I'm going to evaluate my integral. I'm going to factor out my negative 1/2. I get cosine of pi squared minus cosine of 0 squared. Well, the cosine of 0 is equal to 1, so I get negative 1/2 cosine of pi squared. I can't evaluate that. There's no exact value for that because it's not pi, it's pi squared. And then minus 1, and that represents my definite integral. Okay, so that represents the displacement on the antiderivative function. In example 6, this one involves the fundamental theorem of calculus, so FTC. There's two parts to it, and the part that we're going to use is that the integral and derivative are opposite operations. So if I differentiate big F, I get little f. If I go from right to left and integrate, I go from little f to big F. And I can go back and forth, and in essence, I can do this. I can differentiate and then integrate, and I'm going to get back to where I started. Okay, and vice versa. I can integrate, then differentiate, and I'm back to where I started. So that's the idea that I use here. Okay, I have a derivative in an integral. So really I'm just going to end up with the expression that I started with here, and it's going to look like this. So the answer is going to look like log sine. Now that becomes x, and over square root x minus 8. Okay, so that t becomes x. And there's a reason for that, and I'll explain that in a second. But this is really what we're doing. As long as my bound is just x, okay, now it's different if that end bound is going to be some function, then we have to do something slightly different. But if it's just x, we can just replace the t's with x's, and there it is. Now, this a value is arbitrary. Okay, it doesn't really matter where it is, as long as we start somewhere, we end up with this expression. And basically, we're following the fact that I'm integrating. Okay, so I'm integrating here, I'm differentiating, I'm doing both operations, so I should end where I started. So I'm going to explain this just a little bit more in depth. So first of all, just make sure you're clear. This is my answer for this problem. Okay, but there's a reason why we end up with that answer, and it's this. So if I think about what's actually happening, okay, I have this function inside here, and I'm going to integrate from a to x. That means I'm going to find the area. So I haven't done the derivative part of this yet. And if I integrate, I'm going to find the antiderivative. Now, this antiderivative, we don't know what it is. However, we know we're going to anti-differentiate it from a to x. This is t. That's my antiderivative function of that inside. Okay. Now, I differentiate that. Well, first of all, I evaluate this integral. This is why the x ends up replacing the t. We're going to put the end bound in there, and we're going to put the starting bound in here, and there it is. Although we don't know what big F is, we know it looks like that as a definite integral. And when I differentiate this, if I take just this part here, well, I'm taking the derivative of an integral. I'm going to just end up with the original F, in this case with an x now, not a t. And in this case, it's going to be log sine t, or sine x, over square root x minus 8. And that's it. Because when I differentiate that f of a, because a is some number, that is, f of a is a number, that differentiates to 0, so we don't really need to write that in. So that's why we end up with that expression. Okay, so there it is. This is a fundamental theorem of calculus where the derivative and integral undo each other.